To make reliable inference from your models and your data analysis, you have to understand your data right. So let's say we have a data set. Our data set includes many observations, and these points are representing the observations. At a minimum, the observations will include covariate values. What we mean by covariates are the independent features or variables that represent the data points. So for example, our observations could be 3 observations like in this table. Of course, in the green points there are many, but let's say we are focusing on 3 of them. And they have values in 3 dimensions. So the x1 value for observation 1 is 120, the x2 value for observation 1 is 50, the x3 value for observation 1 is 10. So this type of data doesn't include anything except independent variables, the data that we are collecting with no outcome or no response variable. For this type of data, clustering analysis can be done. Because for clustering analysis, we're not interested to see an outcome variable. Actually, we're trying to kind of divide the data set into classes or clusters or groups based on how similar every observation is to the other observations in the data set. It could be implemented in a recommender system. So for example, if we're trying to build a recommender for people's purchases, we're not interested in an outcome variable, we're just interested in a trend of features. If he bought this thing and he bought the other thing and the other customer bought similar things, then we're trying to match those to kind of recommend what is being bought. So this type of machine learning models can fit data that only have covariates, that doesn't have anything else. So for example, these covariates could be representing height, weight, age. So now we have observation 1 with a height of 120, a weight of 50, and an age of 10. Now, usually you would have an outcome variable. So in your data set, there is some outcome variable that you are trying to kind of relate to the covariates or the independent variables that you have. So if we take the same observations, let's say we had an outcome variable from x1, x2, x3 as independent variables, and our outcome variable y was to describe the kind of the weight status of that person, if he's overweight or she's healthy or he's at risk or not. And from the covariates that are given with every observation, there is an outcome associated with that observation. So for this type of data where the outcome variable is categorical, as we see here there are different categories, we can do classification. We can build some of the models that we learned in this channel that can help us classify any new observation given its independent variables or covariates to a category of overweight, healthy, or at risk, or whatever categories we have in our data set. Also, this outcome variable could be a continuous number. So for example here with the same problem, if y is representing the BMI, which is a function of the height and weight and sometimes even the age, we can see from the BMI here a certain value that is related to the 3 numbers that are given in the independent variable. For such type of outcome variable, we can do regression. Because right now we have independent variables that are describing or that are related to an outcome variable that is continuous. So we can perform a regression because our outcome variable is not categorical anymore. Even though you can do regression for categorical variable, but usually you would do some of the classification models. For some problem like this, it's much easier to just build a regression model with the 3 variables and some maybe interaction terms of these 3 variables to predict the outcome variable of a continuous kind of value. Now we described a few things, a few values that we have seen that are related to the covariates and the independent or the dependent variable. So these are called random variables. So in our data set, we have something called a random variable representing every kind of column in our data set. If we assume that the observation are the rows, every column in the data set is a random variable. This random variable could be an independent random variable, sometimes called covariate, sometimes called a predictor, sometimes called an input, if we're talking about, for example, a neural network, a predictor because we're trying to predict the outcome variable using that variable. And also another type of the variables that we have in our data set is the dependent variable, which we sometimes have and sometimes don't have. But if we have it, it's also called the outcome variable, it's called the response variable, and it's called the output variable if, for example, it was a network with an output. This random variable, whether it's independent or dependent, can be either quantitative or qualitative. Quantitative is a numerical value that is representing a random variable. Qualitative is something that we described that is not necessarily intuitively numerical. Even though it's represented in the data set in the end or in the model as numbers, these numbers have a qualitative value rather than a numerical value. Now for the quantitative variable, the variable can either be continuous or discrete. It cannot be anything else. It's either a continuous quantitative variable or a discrete quantitative variable. In a continuous quantitative variable, we have an infinite number of possibilities. So for example, if we are measuring the weight with a very highly accurate scale, the weight can be 76.325, it can be 76.326, and all of these points in between. So it's an infinite range of values that are represented by a number. So the number can have points, it's usually a double or a float in terms of the data type that we have reserved for that field. So you can imagine it like a measuring scale or a measuring stick. Basically, it has different values. It can be of any specific value, even though our measuring stick could have a specific accuracy. However, the actual value can be anything in that domain. And for such things, we can utilize regression, we can utilize different models that only work with continuous data. Now in the discrete case, we actually have whole numbers. So our variable type in that field would be an integer, as opposed to like a double or a float. So for that integer, it could be representing, for example, the count of number of fish fished when that person went fishing, when observation 1 went fishing, when observation 2 went fishing. So this type of data, you could utilize different models to kind of predict the outcome variable. For example, here we can use a Poisson regression to kind of predict the count. So the idea here is that your data kind of dictate what type of analysis or what type of models you can fit. Now for the qualitative. So the qualitative, even though the values eventually are numerical, they are actually not representing a numerical value. So for example, with the ordinal, our data has a specific order. So for example, first, second, third value. By this, for example, cellular bar chart kind of gives us an indication. So 3 cells is better than 2 cells. 4 cells is better than 3 cells. So there is a relation between the category and the next category. And for this, you can do different types of classification or regression models that fit the ordinal data. So make sure if your data is ordinal, you're not just randomly using a simple linear regression and assuming that it's going to work. Because if you're going to develop a reliable inference, you need to use the type of regression or the type of classification technique that fits ordinal data. Now nominal data, it's the same thing, it's different categories or classes, but the classes don't have an actual value, so no class is better than the other. We could look into this number wheel, so no one can say that green is better than blue or yellow is better than red. So each value is different value. So for example, A, B, C, the letters of the alphabet, if you're trying to classify them, they don't have none of them is above the other. So they all have kind of equal weight, but each value is a class on its own. So a classification problem would utilize a nominal output variable where you would try to classify into different classes. So the message here is that your data dictates what analysis you can do with this data. Now, if you're new to the channel, make sure that you subscribe because we cover a lot of videos that will help you grow your skills very quickly. And go watch the previous videos, they will help you a lot. And with this, we end the video on data types. If you liked it, please hit the like button, share it with others so they can all benefit from it. And don't forget to subscribe to get all the new material that we are covering in the channel. Good luck with your data analysis.